Hi Year 12. These videos are going to round off the forces in motion chapter we've been looking at for mechanics. This next part for today is connected particles. That's where you've got, obviously, as the name suggests, multiple particles connected together in some way, and we're going to be resolving forces and what to do in that situation, okay? And it's exercise 10E, this part of the video is going to address. So this is very similar to the Dr. Frost PowerPoint if you want to use that as well. It might have some extra details in it that might make it a bit easier to understand. But yes, as I've said, we're going to have a system that's more than one particle connected together. And you've normally got two choices when you've got a question like this. You either separate your system into two separate pieces and look at them separately, or it might be more manageable to look at the whole thing as one big particle, okay, one big system. Okay, typically if they're moving in a straight line, both of the particles, it's easier to do it that way. Okay, you're going to be coming across two forces, well, one really, but there's two to be thinking about, and that is these two. Okay, so typically tension is a pulling force. If you've got something attached with a string and you're pulling it along, then you're going to have tension in the string. And thrust, which is a lot less of a common occurrence in these questions, is a pushing force. Okay, if you're pushing something along, then the name for it is thrust. Okay, so just bear those two things in mind. So let's see some examples, shall we? I'm going to get rid of these. Well, I might as well read it through. So two particles, these are masses, they're connected by a light inextensible string. Now these two words are going to have modelling assumptions associated with them, and I think that's one of the questions we're going to look at. So we'll come back to what these two things will imply about the model. Horizontal pulling force of 40 newtons. The plane is rough, which means there'll be some kind of friction. Particle P experiences a frictional force, there it is, 10 newtons. Particle Q experiences a frictional force of 6 newtons. So we're going to draw a picture of this, and then answer these three questions here. Okay, the acceleration, the tension in the string, and talking about these modelling assumptions that I've outlined up there. Okay, so here's the diagram. So you've got your horizontal thing that's resting on. There's your two particles. Doesn't particularly matter which way round they go, but it's done Q then P. They're connected by this string. You've got the 40 newtons across that way, and it's being opposed by a frictional force of 10. That's for particle P. The weight of P is 5g because the mass of P is 5 kilograms. Because it's resting on this plane, you've got this normal reaction force, but we don't really need that for this question. You've got tension in the string. That's important to recognise. That needs to go on. Okay, so because of that pulling force between the particles, you've got tension. And because the string is light and there's no mass, that means the tension throughout the string is going to be the same all the way through. So when we come to particle Q, there's going to be an equal amount of tension pulling out that way as well. But let's just put the rest of the forces on. 6 newtons, 3g for the weight, normal reaction force, and there it is. Look, tension is the same. Okay. Make sure that your tension pulls away from your objects. Okay. Try to point it in the right direction. All right, so the whole system is accelerating, okay? It's being pulled along this way, and we're finding out the acceleration. Now, the acceleration is the same for both of these particles, and that's because the string is inextensible, all right? Because this doesn't get, it doesn't extend, it doesn't get shorter or longer, then when these particles accelerate, they'll accelerate the same, okay? So we're going to do the first one, acceleration. I've got a fair few unknowns in this system at the moment. I've got these tensions that I don't know yet, and I want to work out the acceleration. But because these are pointing in opposing directions, it makes sense to treat the whole system as a whole, because then when you form your equation, these t's will cancel out. Okay? If you just think of one part of this system and resolve on just this portion, for example, then you're going to have an equation with t and a in it, which you don't want. Okay, so it makes sense to treat the whole system as a whole. So let's do that. We're going to resolve to the right in the direction of the acceleration and write down everything that goes in that direction or against it. That's all the red stuff in red with the acceleration as well. We're going to write our equation. Remember, it's Newton's second law from last time. Okay, F equals ma. Sum all the forces together and sub your values in. So you've got 40 minus 10 minus 6. The t's are going to cancel out, so we don't need those. And it's 8 times a, 8 being 3 kilograms plus 5 kilograms, and a is the acceleration we want. Work it out, and a is 3. Okay, so if 8a was 24, a is 3. Okay, good. That can go on our picture. The tension in the string. Well, now I can't take the whole system as a whole again because of this cancelling out that's going to go on. I don't want to happen this time. So I'm going to pick a particle to resolve on separately. I can choose to do just particle Q, and that'll be all of this stuff, all of the forces acting on Q, or I could do all of this stuff, okay, all of the forces acting on P. Now, I would have personally have chosen Q because it looks a lot simpler. Okay, there's less going on in terms of the forces, but I think this PowerPoint is going to do particle P, which is fine. So let's do that. Resolve to the right on P. These are the only forces we need to look at this time. Newton's second law again. Sub in your values, 40 minus 10 minus T as well, equals mass is 5 kilograms, acceleration we now know is 3. Simplify it down, and T is 15 newtons. Okay, so that's those two figured out. We have talked about these modelling assumptions, but I'm going to draw it all together for you, and you can write them down. So if the string between these things is light, which it normally will be, okay, I don't think I've seen a question where the string isn't light. There's no mass in the string, which goes on to imply that the tension is the same all the way through. Okay, so the tension pulling out of Q is the same as the tension pulling out of P. The fact it's inextensible means that the acceleration is the same on both particles. Okay, they're both moving with the same acceleration, okay, because that's not getting any shorter or longer. Okay, let's do another example. Okay, this is a different one. This is a scale pan. This is quite a common question to see in exams, and it relies quite heavily on what's in this black box here. Okay, this is Newton's third law. For every action, there's an equal and opposite reaction. Okay, and it can be quite difficult to understand this concept because of like little subtleties that kind of creep into these questions. But it's worth you doing a lot of practice on it to get the hang of it. Let's have a look at what we've got. Light scale pan attached to a vertical light inextensible string. Very similar language for a lot of these. The scale pan carries two masses, A and B. A looks like it's smaller than B, and A rests on top of B. So let's draw this pan, and then we'll see what we have to answer as well. Acceleration of 0.5. Find the tension in the string. Find the force acted on mass B by mass A, and on mass B by the scale pan. Now these two are the ones that rely on this third law here. Okay, but we'll come to it in a minute. So here's the diagram. There's the scale pan. This is the kind of thing it's talking about. There's going to be tension in this string pulling upwards. Okay, these are the two blocks. A is resting on top of B. We can put their weights on. 0.4 g is A's weight, and 0.6 g is B's weight. Remember, it's got to be in kilograms, and these are in grams. That's why it's 0 points. And then we've also got this acceleration of 0.5 meters per second squared. So there's your diagram. Okay, we want the tension in the string. This tension is, in fact, affected by these weights of these blocks. So you've got to treat the whole system as a whole because you've got to consider all of the forces acting on the scale pan, okay? So let's resolve vertically towards the acceleration. Plug in your values, okay? T minus these two equals the combined mass this time, okay? If you've got multiple objects, make sure you combine the masses. So there's the forces. The mass is 1. Okay, and the acceleration is 0.5. 1 kilogram, okay. So there you go. And then everything is a constant apart from t. You can figure out t in terms of g. And then you can work out that it's 10.3. And then that can go on the picture. Okay, the force exerted on mass B by mass A. You've got to be careful here about which object you focus on. And make sure that you include all of the relevant forces acting on that object. And we're going to use Newton's third law as well. Right, so this is what it says. You can't consider mass B on its own because you've got a force that B acts on the scale pan with, and the scale pan acts on B with the same force. Okay, but we don't know how big that force is. Okay, but we know that it's there according to Newton's third law. Okay, force down is opposed by a force upwards. However, what we can do is we can look at mass A, which is exerting a force on mass B, and B is exerting a force back on force A with the same amount. So we're going to look at mass A. Helps to draw a picture to see what's going on, maybe draw it a bit bigger when you make some notes. A has a weight, 0.4 g still, and then B is exerting a force on block A, which we don't know yet. Okay, that's the normal reaction force there. So also got this acceleration of 0.5. We can put that on there as well. And then we're going to resolve on A using second law as well. Subbing the forces acting on A, you've got R minus 0.4g equals the mass is 0.4, acceleration there. And we can calculate 4.1 newtons. Okay, so this force here, this is the force that B exerts on block A. But then from Newton's third law, we can deduce that there's an equal force of A acting downwards onto B. So that's going to help us do the next part of the question. And that's what it says there. Okay, the masses are staying together, so that's what causes us to deduce this. Right, okay, force exerted on mass B by the scale pan. So now we've got this extra force here that adds to our diagram for mass B. So let's draw that again. Diagram of B weighing down the scale pan. 0.6g is the weight of the block, but then there's also this other force acting downwards from the previous part of the question, okay, 4.1 newtons. And then there's a force acting on B by the scale pan. That's the thing that we want to work out. We don't know what it is yet, so we're going to call it S because we used R in the previous question. And then finally acceleration as well. Okay, then resolving forces on B. Everything's constant apart from S. You can use second law, plug the things in. There's the values. Upwards is positive. Solve for S, 10.3 newtons. Okay, so it's quite difficult to do these questions. They are quite common in past paper questions, and it takes quite a while to get a hang of how to use this third law, but there's a pretty decent example of how to do it. Okay, best of luck and have a great day.